Hey everyone, welcome. Today we're going to crack a secret code. It's a language used by pilots, physicists, and even video game designers to describe our world. It's the language of direction, and it's written in these cool little arrows called vectors. But to really get why this is so powerful, let's kick things off with a little thought experiment.
So, what do you think? Would you find it? Probably not, right? You'd just be standing there looking around thinking, okay, 100 paces, but which way? That one missing piece of the puzzle, the direction, is exactly why vectors are so incredibly important.
So to get to the bottom of our treasure map problem, we need to understand something fundamental. In the world of physics and math, there are basically two different ways we talk about quantities. It's kind of like a tale of two different types of measurement.
Okay, on one hand, you've got something called a scalar. Now, a scalar is super simple. It just has a magnitude, a size, a number. It answers the question, how much? But then you have its cooler, more informative sibling, the vector. A vector has both a magnitude and a direction. It answers how much and which way.
And you know what's funny? We use these ideas every single day without even thinking about it. Your age? That's a scalar. It's just a number. But weight, which is the force of gravity pulling you down, that's a vector. And here's the classic example. The speed of your car is a scalar, but its velocity, like say 5 meters per second heading west, that's a vector. It's all about that extra layer of crucial information.
Okay, so if a vector is this powerful instruction that tells you how much and which way, how do you, write it down? Well, the really cool thing is you don't really write it, you draw it. And what's so brilliant about this is just how simple and elegant it is. A vector is just an arrow. The length of that arrow tells you its magnitude, that's the how much part, and the pointy arrowhead, well, that shows you its direction, the which way part. And just like that, one single drawing packs in both pieces of information we need. It's perfect.
So look at this. This one little arrow, that's a whole instruction right there. It's not just some random line on a page, it's a piece of data. This arrow could be telling a rocket which way to go and how much thrust to use, or telling an animator exactly how a character should jump across the screen.
All right, to really make the difference between a scalar and a vector crystal clear, let's walk through a little story. We're going to follow someone, let's say it's you, on a short and slightly forgetful trip to school.
Okay, so picture it. You head out of your house in the morning. You walk a nice straight path, 5 blocks east, and boom, you're at school. Simple enough, right?
But then, oh no, that sinking feeling hits you. You forgot your homework. So you have to turn right around and walk those same 5 blocks, but this time you're heading west, all the way back home.
You grab your homework, and you make that trip one last time. Another 5 blocks east, and you're finally back at school, ready for the day. Okay, after all that walking back and forth, here's the big question. How far did you actually travel? Well, the answer totally depends on whether you're asking for a scalar or a vector. Let's compare the total distance you walked versus your final displacement.
First, the total distance. This is a scalar, so it's super simple. It doesn't care about direction at all, it just adds up every single step you took. So that's 5 blocks there, 5 blocks back home, and 5 blocks to school again. Add it all up, and you get a grand total of 15 blocks. Your fitness tracker would be very proud.
But your displacement, that's a vector, and it tells a completely different story. It only cares about 2 things, where you started and where you ended up. From a vector's point of view, that 5-block trip east and that 5-block trip west were equal and opposite, so they just, poof, cancel each other out. Your final displacement is simply 5 blocks east. See, that's the power of direction.
This whole idea of combining different parts of a journey, it leads us right into the next logical step. How do you actually add these instructions, these vectors, together to figure out the final result?
And honestly, this quote from Physics LibreText just nails it. Adding vectors is basically walking along the path the vectors lay out for you. It's not some abstract, scary math problem. It's literally just following the directions and seeing where you end up.
So probably the most intuitive way to do this is called the tip-to-tail method. It's exactly what it sounds like. You draw your first vector, then you take the start of your second vector, the tail, and stick it onto the end of the first one, the tip. You just keep chaining them together like that, and your final answer? It's the shortcut. A brand new arrow drawn from the very start of your journey to the very end. But wait, there's another way. Following a path is great, but there's another clever trick for adding vectors, and it's especially handy when you have a couple of forces, say, pushing on the same thing at the same time.
First, let's give that final shortcut vector its proper name. It's called the resultant vector. It's the single vector that perfectly represents the combined effect of all the other little vectors put together.
And this other method is called the parallelogram rule. So instead of lining up your arrows one after the other, tip to tail, you place them both so they start at the exact same point, tail to tail. Then you just sketch out a parallelogram using those two arrows as the sides. The resultant vector? It's just a diagonal that cuts across the parallelogram starting from that same origin point. You get the exact same answer, it's just a different way of visualizing it.
And that's the thing. Once you know what to look for, you start seeing vectors absolutely everywhere. They're describing the wind on a weather map, the forces holding up a bridge, the movement of a character in your favorite video game, and yep, even the path to some long-lost treasure. So now that you can read this secret language, the only question left is, where are you going to spot it next?